Thanks a lot. So for today, I was basically asked to zoom in a little bit more on the, let's say, the eyes of the detector, the parts of the detector that are actually supposed to detect the gamma rays, with some emphasis on preclinical technologies, which is an area where a lot of interesting developments are happening. So basically what I will do is to recap a few of the essential principles, general principles, and then I'll give you an overview of some of the more interesting technology developments. And in the interest of time, I cannot target any coverage for this. I will have to limit myself to a selection. So what that means is that you're going to get a highly personal, biased account of things that I consider of some interest. So on a high level of abstraction, if you look at an imaging, at the acquisition of an image, what are you actually doing? There is some phenomenon in reality that you are interested in. There is some quantity to be measured. Let's assume drug uptake. And you do imaging in order to acquire data. That data is then processed. I think Roger gave a very good account of the image reconstruction process. Data is then distributed to the people who are interested in the data, which is probably you. And you're going to try to make some sense out of those data. What that means is that what you observe is not only a function of the drug uptake or any other phenomenon that you are trying to study, but it's also a function of everything that happens in between the object of study and yourself. And so to make any sense out of what you observe, I think it's very important that you also understand everything that happens to the data in those different steps. So what happens in an imaging system is you have an object, let's say a small animal, that is emitting gamma rays, annihilation quanta or gamma rays from technetium, for example, and those needs to be transferred into an electronic signal first. So for that we use a radiation detector. So the purpose of the purpose of a radiation detector is to convert the energy of the ionizing particles into electronic pulses. That's what it does. And there are many types of radiation detectors. Some of them directly convert the energy into charge. Examples of those are gas field detectors and semiconductors. And many detectors in nuclear medicine work on the principle of scintillation, where you convert the energy into a small flash of light, which is then registered by a photosensor. So let's start with a very simple case. Roger already showed this slide. There are a couple of different processes that can convert ionizing particles into charge. And we are specifically interested in photons, electromagnetic radiation, in particular gamma radiation. And the two effects that are of interest to us are the photoelectric effect, where the photon basically kicks out an electron from an atom, and the Compton effect, where the photon gives a part of its energy to kick out an electron, and a second photon is created which travels along with a lower energy and in a different direction. So what we have here is electrons that have been kicked out of their orbit, and of course we also have ions. The remaining atoms are being ionized. And this is used in gas field detectors. Very simply, the principle is that in a volume of gas, if you apply an electric field over that volume, what will happen after a particle creates these ionizations is that the electrons will move in one way and the ions will move in the other way. And together, that gives you an electric signal. And one example that is probably well known to you is the good old well-type chamber that you might have at your labs to determine the amount of activity you are injecting. That works according to this principle. You can essentially do the same thing in a semiconductor, where the terminology changes a little bit. The physics is essentially still the same. We are kicking out electrons from atoms. Those electrons form part of the signal. But now we do not have any ions left because all the atoms are stuck in a crystal lattice. and we speak of holes. That's the, let's say, the empty spaces where an electron used to be. Now, if I have a piece of semiconductor and I reverse bias it using a voltage source, then what I will do is I will have the electrons moving in one direction and the holes moving in the other direction. So it's more or less the same principle, but now in a solid material. And again, I have a signal. This principle is used in quite a few types of radiation detectors, notably in radiography, digital radiography, where, for example, such direct converters are being used. We also encounter such systems in preclinical systems. This is one nice example of a cadmium zinc telluride detector. That's a semiconductor, which you can obtain in the form of a pixelated detector. So it consists of a 2D array of CZT pixels, which are then read out individually in order to get a 2D position-sensitive radiation detector. Unfortunately, I don't have a lot of time to focus on this very interesting class of detectors, because today the scintillation detector is still the type of detector that is most often used in our field of science. So I'll spend a little bit more time on the scintillation detector. As I said already, the scintillation detector comprises two parts. It's a scintillator and a photosensor. So the scintillator is usually a transparent material, a crystal, that has the interesting feature that it can convert the energy of ionizing particles into optical photons. So you have small, tiny flashes of light, and those optical photons are then registered by means of a photosensor. And then you have an electric signal that you can work with. So, what you already showed, the photomultiplier tube, that is still the photosensor that is most oftenly used to detect the optical photons. It's capable of detecting single optical photons, and in a scintillation flash you might have a few thousand to perhaps more than 10,000 of those optical photons. And a part of those are converted into electrons by the photocathode, and such a photoelectron is then accelerated towards a series of dinodes, and it's each dinode, such an electron releases 3 to 6 or so new electrons, and if you repeat that process a couple of times, you end up with a fairly high overall gain, which is more or less constant. So what is important to realize is that in a scintillation detector, the number of photons that's being created is proportional to the energy that was absorbed. So if the gamma photon is fully absorbed, it's actually proportional to the energy of the gamma photon. And then if I apply such a fixed gain, which might be in the order of 10 to the 6th or 10 to the 7th, to the photoelectrons that are being created, I end up with a charge pulse that is again proportional to the energy of the gamma photon. So these photomultipliers are used in nuclear medicine detectors, and one example is shown here. That's basically the simplest case, planar scintigraphy, which you do with a gamma camera. And in such a camera, a number of PMTs are optically glued to a scintillator, and quite often there is actually a light guide in between that spreads the light that's generated in the scintillator over a number of these PMTs. And then in front of the camera there is a collimator that accepts only the photons that are incident perpendicular to the device, and so only here in this region you may have some scintillation going on, and that can then be localized by those PMTs. Here you see another picture of the same device. You can imagine that if you have a light flash here in the center, that only the PMTs at the center will give you a signal, and from the ratio of those signals you can estimate where in the scintillator the gamma photon was absorbed. And so in SPECT, we use one or more of these gamma cameras rotating around the patient to acquire a three-dimensional image. Now, if you want to image small animals, a classic gamma camera is not very useful because it will give you an image resolution that is in the order of a centimeter or so. And if you're interested in structures that are rather of the order of millimeters or sub-millimeter, this is not very useful. So one trick that you can play is to use the so-called pinhole camera, using magnification of your image. And that's basically shown here. So in the clinical SPECT camera, you basically have parallel collimators without any magnification, and the image that's being formed, or the projection, if you want, of the object is basically of the same size as the object. Whereas with the pinhole camera, which is basically working along the same principles as the classic pinhole photo camera, except that the pinhole has to be made into a thick layer of lead because it has to collimate the gamma photons, then you will get an enlarged projection of your object at some distance. This principle is used in several systems. This is one of the earlier devices where two pinholes with detectors behind them were looking at the object, the mouse here in the middle, and it was actually the mouse that was rotating in order to obtain projections from several different angles so that you could tomography, and this is one of the images that was acquired with this particular system. Now, as of then, many of these systems have been built, and progress has proceeded to obtain better and better images. And as just one example of such a more modern system, this is the SPECT that actually has a collimator with a large number of these pinholes. And each of these pinholes creates an enlarged projection on one out of the three gamma cameras that are here surrounding the animal. And the interesting thing about this approach is that you don't need a rotation anymore. You have so many projections from that large number of pinholes that you have a stationary device which has, of course, some advantages. So, most recent result, this is some images that the inventor of this device, Freek Beekman, sent me last week. I think it's quite impressive. They are now able to reconstruct the images with a spatial resolution of about 1/4 of a millimeter, which I think at this moment is the best resolution that is being achieved in nuclear medicine in general. So that was SPECT, and the other important imaging modality is PET. As was explained already, PET operates on the principle of coincident detection of annihilation photon pairs that are created in the annihilation of a positron with an electron in the object under study. And the classic PET detector ring, as you find it in the clinics even today, comprises a large number of these so-called block detectors, which typically comprise an array of, for example, 64 scintillation elements, each having a diameter in the order of about 4 millimeters, connected to some 4 photomultipliers. And also these detectors rely on the principle of light sharing, and a large number of those are put in a ring. So looking at that detector, the operating principle is basically light sharing. If you take a good look, if I have an event here in the corner of the crystal, I may have this photomultiplier giving me the largest signal. So let me try to repeat that for you. The event is taking place here. Most of the light will be channeled backwards to this PMT. And now if I have an event taking place more towards the middle, then you can imagine that these two photomultipliers are going to give signals that are more or less of equal intensity. And according to that principle, I can basically, for each of the crystals in my array, determine which ratio of signals corresponds with that and I can identify which crystal has been hit using only 4 PMTs to read out this entire block of crystals, which is a very efficient approach. Now, if we want to do small animal PET, we have to worry again about resolution. And in PET, there are some factors that contribute to the resolution, and some very fundamental ones are indicated in this slide. First of all, the positron, needs to travel a little bit in order to cool down, to lose its energy until it is almost in rest, and only then it can annihilate with an electron. That takes a little distance typically, typically 1 millimeter or a few tenths of a millimeter before it has slowed down enough to be able to annihilate. And then when it annihilates, 2 511 keV annihilation photons are being emitted in almost opposite directions. Almost, but not quite. This principle is governed by the conservation of momentum principle, and the problem is that the electron is typically bound to an atom, which means that its momentum is not zero. And so the momentum has to be still preserved by the 2 511 keV photons, and you will see that the emission angles vary a little bit, typically by about half a degree. So there is always a little error in my line of response that comes from that. Then there is a third factor that contributes to spatial resolution, which is the interactions in the crystal. Here again, we rely on the photoelectric effect and content scattering, and quite often, especially in PET, multiple events have to take place before the photon is fully absorbed. So you can be lucky and have a photoelectric effect going on right on the first hit, but that actually happens typically only in about 30% of the cases. And in all other cases, you will start with a Compton scatter, maybe have a second Compton, and only then have a photoelectron being generated as indicated in this image. So that means if all of this happens in the same crystal, which requires a fairly large crystal, you have multiple energy depositions in that crystal. But in PET we typically use fairly small crystals, so what may happen is that only the first event takes place in my small crystal, and then a Compton photon travels on to another crystal where it will deposit more energy. And so this is something to take into account when you assess resolution. Now Simon Cherry made some very nice simulations of all of these phenomena. And what he showed is that in a whole body scanner, which typically has a large ring diameter of about 80 centimeters, you see that the biggest contribution to the overall resolution is actually the non-collinearity. So that error in the angles between the two annihilation quanta is not very large. It's only about half a degree, but it's magnified by the large distance that the gammas have to travel, and therefore the overall resolution in clinical PET almost by definition cannot be better than about 2 millimeters. Now if you would make a smaller scanner, let's say with a diameter of about 30 centimeters, which could be a brain scanner, then you will see that that error gets a lot smaller, and you might be able to get sub-millimeter resolution. And if you want to image a mouse, it makes sense to make your scanner even smaller in radius, and then this non-collinearity contribution can be made very small. And what you will see is that at that point, actually the interactions in the crystals will start to become the dominating factor in the resolution. But in principle, it should also be possible, according to Simon, to get resolutions better than about half a millimeter, based on this theoretical analysis. Now, in the last years, many people have tried to actually come close to those numbers, and it's not very easy. But in the remainder of this talk, I'm going to show you a few approaches aimed at getting us close to that kind of numbers. Before I go there, I need to explain to you that there is one more factor that can affect the resolution, which is the so-called parallax error or depth of interaction error. In PET, we need fairly thick crystals because we need to absorb the 511 keV photons, which means that a crystal typically needs a thickness of some 2 to 3 centimeters to efficiently absorb all the gamma photons. And that means that if your crystals are not aligned exactly perpendicular to the direction of the photons, and you don't know at which depth it has been absorbed, you get an additional uncertainty as to where exactly your line of response is. So what that means is that if you image an ideal point source in the center of your scanner, you will get a nice circular image of your point source. But if you put the same point source somewhere at the edge of the field of view, you get a large parallax error, and you will see something like this. It gets more egg-shaped, so there is a bias in your image, a systematic error, and there is also more blurring, so the point source appears to be larger than it really is. And one way to avoid this error, of course, is to actually measure the depth of interaction in your crystal so that you, again, know exactly where your line of response is. And some interesting approaches towards that are shown here. People have tried all kinds of different things to accomplish this depth of interaction detection. One straightforward method almost is to make your crystals in multiple layers and apply some offset between these different layers. And then what will happen if the gamma photon is absorbed in the top layer in this two-layer system here, then the light from this crystal will be spread through these two crystals right below it towards the photosensor. Whereas if it is absorbed in the lower crystal, it will only go down here. So again, you're able to decode which crystal has been hit. And another interesting approach is the so-called phosphate detector, where you use different scintillation materials stacked on top of each other, and you can see by the pulse shape that is created which type of material has been hit, and therefore you are able to decode which of the two layers must have been hit. Another variety on that is to actually apply a phosphor on the upper half of the crystals, which converts some of the light into a pulse with a slightly different shape, probably also a different wavelength, but what we use is the shape of the pulse, and that gives you, again, a way to decode the depth. And finally, another approach is to read out the crystals from two sides, and then from the ratio of the signals on the both sides, you can decode at which depth the crystal has been hit, at least in principle. So these are, let's say, geometric solutions to decode at which depth the crystals have been hit. And as you can imagine, that requires photosensors that are a little bit more refined than the classic photomultiplier that's used in clinical PET systems. And one system that has triggered, or one device that has triggered a lot of this research in the last 2 decades is the so-called multi-anode PMT, which is basically a PMT where the anode is split in pixels, and this is an example of a device which has still one photocathode, but which is read out by 8x8 of these dianode and anode structures. So essentially what it is a 64 pixel PMT. So on the back there is 64 outputs that can give you signals. Today we also rely more and more on semiconductor photosensors. One device is indicated here, that's the so-called avalanche photodiode. It has the important advantage that it is a very compact device. It's made out of silicon, maybe less than 0.5 millimeter thick, which also has the advantage that this actually is very transparent to the gamma rays, so you're not forced to put it at the back of the detector. You can also put it in front of the detector. If you remember the double-sided readout approach, this is of course a very important properties, and indeed this approach was tested first with APDs. Now today we have an even more sophisticated device which is called a silicon photomultiplier, and without going into its operating principle in a lot of detail, what it does for you is give you a gain which is quite comparable to the classic photomultiplier. It's in the order of 10 to the 6th, but it is still a semiconductor device which is highly compact, can be operated in magnetic fields if you want to combine it with MR, and has other very nice properties. So a lot of new developments are basically based on silicon photomultipliers. One of the new developments there is the so-called monolithic scintillator approach, where basically we no longer segment the crystal, but we leave the scintillator intact. So we use a block of scintillation material, which is typically a few centimeters on each side. And then we read it out with a light sensor, which might be a silicon PM array or an APD array, or even a multi-anode photomultiplier, that gives you the distribution of light as measured on this surface of the crystal. And you can probably intuitively understand that if you change the position of interaction in this transparent material, that the light that's projected on the sensor will change its shape depending on the position of interaction. And interestingly, the shape is also a function of the depth of interaction. So if the event happens further away from the sensor, you will get a broader light distribution compared to when you have an event that happens very close to your sensor. So at least in theory, we should be able to decode the three-dimensional position of interaction in the scintillator from the light distribution that's measured on only one of its surfaces. Of course, you can also read out the scintillator from multiple surfaces if you think that will give you a better result. And there are quite a few groups, including my own group in Delft, that have performed a lot of research on this concept in the last years. This is what it looks like in practice. Again, you have here your monolithic scintillator mounted on an array of photosensors. In this case, it's an array of digital silicon photomultipliers. You can see that the crystal is actually smaller than the array. That's because we are playing around with aspect ratios and so on. And then the trick is really in the way how you do the decoding, how you estimate your position of interaction from the signals. That's where the clever bit is, and where a lot of research is being done. This can give quite nice results. This is one example, this particular example that you just saw with the digital silicon photomultipliers. And if you compare its performance to the detectors that are now used in clinical PET systems, you will see that it has much better spatial resolution, can be as good as 1 millimeter. It has depth of interaction resolution, which the classical PET detector has not. And especially the timing resolution can also be very good. Less than 200 picoseconds compared to more than 500 in PMT-based systems. So this looks very interesting for clinical PET, perhaps also brain PET and so on. But as you can see, for preclinical PET, you might still want to have somewhat better spatial resolution than the about 1 millimeter resolution that you can get with this type of detector. And then a development that comes from Japan, I think, is very interesting. This is an approach that is investigated at NIRS near Tokyo in Japan by Yamaha's group. And what he does is basically by laser engraving, he kind of structures the monolithic scintillator into a three-dimensional array of very tiny cubes, and each of those cubes is about 1 millimeter. And the effect of that is that the light is now channeled along either the rows or the columns of that crystal, so it reaches your sensors in a more focused way than is the case in the classic monolithic scintillator, where the light can travel more freely. So this is an example of such a block that's laser engraved. You can see how there is a structure, kind of a matrix structure of reflecting layers now in the crystal. And this appears to work very well. Again, using SIPMs, they were able to make these three-dimensional histograms where each of the 1 by 1 by 1 millimeter elements in this detector is quite clearly resolved. I think it's a very impressive result. And then finally, another interesting research line here in the US is performed at UC Davis by the group of Simon Cherry, where he is in principle following a somewhat more classic approach. Crystals that are cut to very long and thin needles, if you want. These crystals are really very, very tiny in diameter. As you can see, in the order of 0.5 millimeter, and there is reflector foils in between. And as you can see in the image here and also here, these crystals are actually tapered. So they look at the object and they become a bit broader when you go to the back. And that's to reach an efficient fill factor in the ring. Of course, this ring is very small, so if you don't use the taper, you're going to get pretty large triangular dead areas in between your detector modules. And of course, this gives you an enormous number of channels in your system. And to deal with that, he is using so-called position-sensitive APDs. Again, a variety of the new semiconductor photosensors to read out these crystals in an efficient way. And some of his latest results are very, very impressive. This gives you an image of a micro-resolution phantom, where he achieved a resolution of about less than 0.6 millimeters, in fact. I think that's really, really impressive. So that was my talk. I don't know, Chairman, if you want to allow questions or move on.